Is that not going to break?
Elastic.
Is it? Okay, stationary waves. Right. Okay, so a couple of things to look at, but anyways, we'll get started. Another name for stationary wave is standing wave. Maybe somebody's heard of that before. Any ideas? Stationary or standing wave? Now resist the urge to say anything stupid, okay? No. Not quite. Not too far away, but not quite. Anybody else heard of this before? Yeah, what do you think it is? Do you remember? Nearly. You're not too far off, but it's kind of the verb, the moving. Like they are moving. Go on, yeah. Seems kind of stationary. What were you going to say? It's not really propagating anywhere, is it? I think you have the picture in your mind. It's kind of in one place, but it'd be wrong to say it's not moving because it would be still then. But it looks like kind of it's not moving. Anyways, a standing wave, also called a stationary wave, so we can write this definition down, is a wave that oscillates in one constant position. And well, we'll get to the reasons why in a moment, so if you can just... Okay. Got that? Yeah? Not yet. Yeah? You can rise in a stationary medium as a result of interference between two waves travelling in opposite directions. It's kind of hard to picture. We were talking about interference last time, how one wave can interfere with another, and then we have the two types of interference, you remember? Mm-hmm. What are the two types? Constructive and destructive. So we have this interference going on, almost the wave with itself. The picture will kind of help here now. You might have seen this before, maybe even in high school, this little machine. It looks like this, but that's only because it's moving so fast. There's actually a wave here on one string, but it's moving up and down so fast it kind of looks like almost like two strings nearly, doesn't it? Has anybody seen this in high school before, this machine? No? Poor school, that's so sad, so sad. Yeah, so what? So what? He could still come from a poor school in China.
Well, he's here.
That's true, actually, yeah.
He kept saying he's bored, and I can't accept that.
Oh, yeah, okay, yeah. Anyways, none of you have seen this before? None of you have seen this before? No? No? Okay.
We are all from poor school.
All from poor school, so sad, so sad. Okay, anyways, I might try to find a YouTube video later to show you this machine, maybe even in slow motion. So, it looks like there's two waves here, but of course there's only the one string here. The way it's vibrating is in such a way that it makes it appear like there's two. This part here of the string is actually vibrating up and down a lot, whereas this part of the string, it almost looks like it's not moving. What's happening is, as the wave tries to move to the right, it's reflected back, and the interference between the two is in such a way to make this effect. You don't really need to know that much detail for the exam. It's just another type of interference. What's really important to know is now the different parts of this wave. So we have a node, which is, well, I don't know if anyone knows this. You know this one?
A point.
Yeah, but which one?
0 point.
Yeah, so what would you, yeah, so the node is the point on the standing wave that has minimum amplitude. In other words, in the picture, probably zero amplitude. It's this one, this point here, this point here, you know. So what do you think you've seen it now, the opposite is called an antinode, and this point has the maximum. So here's a picture I'd like you to draw with the definition, please. It's good to have the picture, because in the exam it will be common enough for them to ask you to draw a standing wave and to label the nodes and antinodes on it. And it's worth pointing out, you notice that the endpoints here also called nodes as well, not just the middle points. Nearly got that. Yeah, just a quick picture as well. It's really just important to know where the nodes and antinodes are on the picture. Okay, so now in a moment, I'm going to ask you to imagine, or can we go to the next slide? Are you sure? Yeah? What's on? Which part are you writing down, Jerry? Okay, quick. Okay, Jerry? Yeah, okay. So, just think before you answer. If you know the distance between the nodes or the antinodes, you could know the wavelength. So, before you say it, just think for a moment. You know the distance between the nodes or the antinodes, so just call that distance D or something. You could get the wavelength from that distance. What would it be? So, yeah, if you were to write that down, what do you think you're saying? That the wavelength equals D over 2? What way around are you saying?
Lambda over 2.
So D equals lambda over 2. Yeah, so lambda equals
2D.
Yeah, so it's very simple to know the wavelength. It's just twice the distance. Very good. Okay, so if you know the distance between the nodes, then you know what the wavelength is. This is something that catches students out in the exam. Sometimes the question gives them the distance between the nodes, and they're not thinking, and they write down that that's the wavelength, okay? So it'd be good to make a note of this, so you don't make that mistake. I don't think I need to draw it, because everybody got it okay. Can you picture that? If we go back to this one. This is actually one wave here. Yeah? So if you know this distance, twice that will be a wavelength. Yeah? Okay, so make a note of that, please. I think the reason students think it's the wavelength is because they're thinking of the other thing, you know, the distance between the crest to the crest or the trough to the trough, so they're just mixing up that idea. Okay, continue? Yep, right. Now, if the string is held at both ends, which it was in the picture, and that you have no movement at the ends, then the ends become nodes, which we know that, and the length of the string then is a measurement for what type, or you could use it as a way to work out what the wavelengths are. The longest wave you can fit is called the fundamental. Let me try and draw that. So, if you have a string like this, you could actually have a few different wavelengths in there. You could, have something that looks like this, or you could have something with a longer wavelength. This is a short wavelength, so maybe you could have something that goes up, down. Okay, that's one, and then you could maybe have another wave in here. But if you think about this, what's the longest wavelength you could make? Well, the longest one would be, something like this. I can't make it any longer than this. So this wave here is called the fundamental. It's the longest wavelength you can fit here. And the problem, I suppose, is because these have to be nodes. I can't, I couldn't do this because it has to be fixed here. So the longest one we can fit, that's called the fundamental. Now the next longest, let's see if we try and draw this. Well, actually, no, I'll let you try. Try and draw in the next longest wavelength. So this one's the longest. I can't make it any longer than this. What would be the next one? If you can try and draw that down.
Come back.
Yes? You think you got it? Well, not quite like this one, but am I getting this right? Can't get anything in between, can I? Because I have to have this fixed. Yeah. So that's the next one then. Okay. Maybe somebody knows the name for this. So obviously there's only one called the fundamental. Do you know? What? Which one? Semi what? Not semi-fundamental or anti or quasi or anything like this. Fundamental.
Die.
Or di-fundamental or bi-fundamental.
Second.
Or second fundamental. No. No.
Fundamental two.
No. No.
Double.
No. None of this.
Mono.
Monomental. No.
Antimen.
Sorry, I said no for that one. Unfortunately, you don't know this. I thought maybe someone might know this. It's actually a different word. Let's see if I got it there. There's harmonics. So, huh? Was it? Really? Alright, okay. The frequencies are also, the multiples of the fundamental are also called harmonics. I think if I remember this correctly, you can call the fundamental is the first harmonic. And then the next one is the second harmonic. And the third harmonic. I think there's another word which we don't use called overtones. Is that right? Overtones? Yeah, but I think they're one out of sync with. So I don't think the first overtone is the same thing as the first harmonic. I think they're off by one. But anyways, it doesn't matter because we don't use overtones in the exam. We just use the word harmonic. So first, second, third harmonic.
What's the harmonic again?
It's just the next one after the like the fundamental is called the first harmonic. Then the next one here, the next biggest wave you can fit in is the second harmonic. Third harmonic is the next one after that. You get? Well, I have a chart coming up that will help here actually. If you want to draw this. So you see, this is the first harmonic, also called the fundamental. This is the second. Whoops. This is the second harmonic, third harmonic, fourth harmonic. This is the longest wavelength, second longest wavelength, third longest wavelength that we can fit. So it's actually useful to have this because sometimes in the exam you need to draw one of these. Like they might say such and such fourth harmonic. It's helpful to actually draw it to work out in your head what the wavelength is. You know, if they tell you, I have the fourth harmonic and this is the distance, you'd have to think a little bit to get the wavelength. Diagram will help you work that out. Is this a new word, or do you remember this from high school? This is new? Okay. Monica, you remember this before? This is new? Okay. Don't be too worried about marking in the nodes. What I really care about from this diagram is getting the right number fit it in.
No, that's too.
Yeah, that looks a bit too many for that one. Yes?
The distance between the nodes and between antinodes is the distance between nodes and antinodes and antinodes.
Again, but slower. The distance between...
I mean the distance you mentioned just now.
Oh yeah, between a node and a node, or an antinode and an antinode.
Which means crest to crest.
Yeah, crest to crest. Well, if you're looking at the antinodes, crest, the crest.
So it's a wavelength.
No, we said that's, yeah, you will need to double that number to get a wavelength.
But our definition for wavelength before is the distance to crest.
I know, and you remember when I was saying this, that a mistake students make is that they mix up that definition with what we're doing today. So, you're right, a wavelength is the crest of the crest, but this is an unusual wave because it's standing still in one place, vibrating up and down. You know?
Yeah.
Oh, sorry, I didn't draw crest to crest when I drew it there earlier. Let me draw this again. Right. Okay. I need to go a little bit more. Okay, so Lee, you're happy that's a wavelength there to there.
Yeah.
But if this is vibrating up and down, I'll just put a dotted line here. It's almost like this is a fake crest nearly. It's not quite the same as what I had in the original picture, kind of. So it'd be wrong to say that that's the wavelength. If you were to think about the original string that's vibrating up and down. Actually, when you look at it, that's only half the wavelength. Yeah? It's okay?
Yeah.
Are you sure?
Uh-huh.
Okay. Did you draw this? Yes? Yes? Okay. Continuing then. So in these particular pictures, there's a node at either end. Left and the right, there's a node. Now, we can have sound waves in pipes and musical instruments like this here. In fact, when we have a sound wave in a pipe like this, there'll always be a node at the closed end, and closed has the same meaning that you think it would, and then there's an antinode at the open end. So just to be clear, what I mean is, if I draw the pipe like this, this here will be a node, and this end here will be an antinode. So the fundamental, the biggest wave I could draw would be not quite that, like that, and that's vibrating up and down. If I call this distance here d, then what would be the wavelength for this picture? Would it be 2?
40.
It would be 4, wouldn't it? Because this is actually, if you think about the cycle, it's only a quarter of the way through it. Are you happy with seeing that?
What you know that?
Yeah, because it starts here and it goes up And if I zoom out here, it still has to come back down. And that's only half.
Why
Still-
half?
Oh, because it can still do this. So this is well, that's not a great picture, but that's one full wave. So I'm only looking at a quarter of it here, because this is like the crest, but the trough doesn't happen until, oh my goodness, all the way out to here. Yeah. Okay, I think it'd be good to draw this into your notebooks, actually. If you can add that in as an example. Tired, Sean? A little. Okay. Do you have that? Yeah? Alright. Yes? Question? No? Okay. This is actually, I get musical notes and all that stuff. This here, yes, I need you to draw this. This is what I was just showing you a moment ago. So this one here is the fundamental. This one here, third harmonic, fifth, seventh, ninth, and so on. Really. And then this one here, I know, first, second, third, fourth, fifth. Yes. If it helps, you don't need to write down the overtones. If it helps.
Why is it different?
In this picture here.
Why the wave is different?
Yeah, because in this picture here it's open at both ends. And you see in this picture it's closed at one end and open at the other end.
Yeah.
So in these pictures these all must be antinodes. It has to be an antinode. Whereas here it must be node, anti, node, anti. Can you see the difference?
So it depends on what kind of instrument.
It does, if it's closed or open.
Because your picture was good, but that's the last one.
I don't really know.
That's the last one.
I just put the picture in. Yeah. You reckon it's this one here? Could be, or maybe it's actually this one here.
No, I'm sure it's left.
You're sure it's left?
I'm playing.
Alright, okay.
It's a left.
Fortunately not important to know for the exam, so it's okay. Don't write down these overtones. You don't, well, you can if you want to, but I think there's enough to write down. Yeah. Okay, so if you can do your very best to draw this into your notebook, please.
So what do you mean when you say this is antinode?
In this here?
Yeah.
What I mean is, it's vibrating up and down here the most. So if you were to look at this, I know it's a sound wave so you can't see it, but if you picture as if it was a string, it would look like it was moving really, really fast here. So you would, if you could see it, you would have something that looks like this. So it's vibrating a lot here, not doing anything here. Yeah.
So we don't have to know the overtone?
No. Well, I've never seen them use this word in the exam. You know, whenever I see them talk about this in the exam, they always use harmonics. Yeah. That's if it was closed at both ends, yeah. But you see, if it's open at one end, it must be an antinode in the picture. So you don't actually have, so you can't actually get the one that you just drew there. So we jump from 1 to 3. Now, we don't use overtones in the exam, but I suppose one advantage of using overtones is you don't have to worry about the numbering. when you draw this, please make sure you have the right number of hills, please. How are we doing drawing this?
How did you make this picture?
I didn't. I got it from Google.
Google?
Yes.
Oh, that means and why do we draw this again?
To help you remember it.
And do we have to draw it?
In the exam, Lee, what will happen is they'll give you some information, like you have a pipe and there's this harmonic formed in it, and they might ask you for the wavelength. So it's very helpful if you can draw the wave inside of it, because then you can work out what the wavelength is. Like in this picture here, if I gave you the length of the pipe, what would be the wavelength? Well, do we have one full wave in here?
No.
No, so we only have 3/4 of a wave. So you would say 3/4 of the wavelength equals this distance. It's not always easy to see that without a picture.
Why is 135
Because we're kind of skipping ones in the middle, nearly.
No.
What do you mean, why?
I mean, the overtone one is 1, 2, 3, 4, 5 harmonic.
Yeah. The overtone numbering is nice.
But the last one we have to draw is 1, 3, 5, 7, 9.
I suppose, like KJ was just asking me here, KJ drew this one. Well, why can't we have that one that's just like this? It finishes on a node, but because this is open, we have to finish on an anti-node. So it's messy.
But not the full field size in nodes, so because it's open, so it's like 3 or 4 waves, so there's a harmony like that. The magnate is actually top part, you know what I'm saying? You know what I'm saying, right?
No, I don't actually. The problem, Chrissy, I suppose, is closed here, open here. So this has to be a node, this has to be an anti-node. Kind of ties your hands a little bit.
Yeah, that's what I'm saying. It's like 2/4 is gonna be second harmonic wave.
2/4.
I mean, if.
Oh, I see. You're trying to see a pattern here. 1/4,
Yeah.
2/4, 3/4.
Yeah, 3/4 waves, so it's third harmonic. 5/4 is fifth harmonic. Is that?
Now that looks good, but then what about here?
I don't know.
So.
I don't care about the
Oh, yeah, okay.
I'm talking about the last one. I mean,
If you're just talking about the left one, you're right. The harmonic number will be the same as the numerator.
Yeah.
Yeah, I suppose let's put those numbers down actually. I think that would be good. So we have first, second, third, fourth, fifth. Sorry. Well, actually, no, I'll put the 3 down, but I'll just skip it. Okay, so 1, we have a quarter. 2, nothing. 3, we have 3/4, nothing. Next one here?
5 over
Yeah.
nothing. 7 over 4.
And these are all wavelengths. So in the first picture here, we have a quarter of the wave. I won't really put land, I'll just write quarter. Here, the first one, we have half. Second one, we have 1. Next one, 2 over 2. Now, if we're trying to get a pattern going, we might not want to quite
2 over 2, so it's 2, right?
close.
Yeah.
No.
You mean for the first one, or for
No.
which one?
Second one.
For the second one.
It's 2 over 2, so that's 1.
It's
Oh, sorry, I skipped it.
No,
Oh, I didn't.
But it's easier that way.
3 over 2. Next one, isn't it?
Yeah.
But you're right, you should want to rewrite this a different way. Yeah, so you see that for this one you should rewrite it as 2 over 2. Okay, well what's the next one then?
That's 2.
Two. 4 over 2.
4 over 2, which is...
2.
So, you've spotted these numbers here. They match up with that, but there's a big difference between the left and the right here. If you're trying to think of a general pattern going on here, this number here, 4,
5.
4, 4, 4, 4, whereas here,
2, 2, 2, 2.
so, it's good, you can go with that.
Memorize, but
It's just one of those things where you think in an exam you'll remember it.
well, I think we don't have to memorize that.
Well, for the exam, they expect you to draw this.
Just the left one, right?
Oh no, the right one as well.
Oh, really?
Yes.
Just say no. Just say let's have it over something.
No, I don't think I said that.
The overtime.
Yes, that's what I said.
Let's take a picture.
Okay. We'll add them to your notebook later, okay?
Uh-huh.
Got that?
Wait.
No, okay. Chrissy, I will tell you though, in the exam, I can't really remember a question where they have a problem with this one. Every time I can think of a past exam question, they always have the pipe closed at one end. So 90% chance that it's going to be this in the exam. But there's nothing in the syllabus that says, oh, it has to be this and not this. You know, so I think it could be either, but they seem to prefer this one in the exam.
But that's real because I cannot think of any instrument is like the right one.
But it doesn't have to be. I just put the picture in.
I have the pipe.
Yes.
Yeah.
But the question doesn't have to be about an instrument.
But you put it.
I know.
Because your fault.
I should replace it with something else then. Got that?
Gotcha.
Yep. Next slide, or no, I still see people writing. You have that?
Yeah.
Are you sure? Chu?
Yeah.
Okay. Now, we have a small little problem though. I don't know if you remember, or if you've ever seen or done this experiment in high school, where you have a pipe, usually fill it up with a bit of water, and you have a tuning fork. You know which one I'm talking about. And what do you do next? Yeah, you strike the tuning fork and then you try to vibrate to get resonance here. And what you're trying to do is to get a standing wave formed in here. So let's imagine that this here is D, and let's just imagine, I don't know, well, I'll get rid of the water just for the moment. We have the fundamental in there. So what would be the wavelength here? Actually, let me just call that L instead of D. Should be 4L. Oh goodness, 4L. But in real life, there's a slight problem. We don't actually get this length here. It doesn't perfectly match up with the 1/4 of the wavelength. So we have this thing called an end correction. It's like there's a small error here that we need to consider. Now, what I find a little bit strange is I don't think it mentions this to consider in the syllabus. However, I have noticed 2 exam questions that have asked or have talked about this end correction before. So I don't really think they should be talking about this, and the new person who's writing the physics exam, the wordy guy, he's very, very particular about making sure the exam questions match up with the syllabus. So I don't think he'll mention this in his exam. But just in case, because it has been in past exams, and maybe he'll look at a past question and make an example from that, we'll just cover exactly what it is. So the end correction, which I'll just call delta L, is the short distance added to the actual length of the pipe. The antinode is not formed exactly at the open then. It's a little bit of a distance away from it. You don't need to write all of this down. I think it's enough really just to write this down, because I'm not going to give you any formula for it. When I was looking this up, there doesn't seem to be one established definite formula to use. There are different formulas you can use, and it depends on the diameter and the radius of the pipe and all these different things, but when it's come up in the past exam, they're not expecting students to know any formula for this. And it's not in the formula book, but I want you to at least know what it's called. End correction, delta L. The short distance added to the actual length of the pipe. Yeah. So it's like an error. When you did this experiment, did you talk about the end correction, or that didn't come up? You don't remember? Because the amount is quite small, so sometimes the teacher doesn't consider it in the experiment. Like it doesn't it changes it enough to notice, but not too much. Yeah? Got that? Yes? I don't need you to write all of this down. So, drawing all those pictures took a lot longer than I thought. We'll split this into 2. So it won't take us the full second class to finish this. We can have some look at some questions, but we'll take a break for a couple of minutes. Then we'll have a look at some of the questions I have. Well, actually, no. Just before we do, there's one actually I want you to do. Let me see. I can't remember it exactly. Okay, so I think I remember these numbers right. We'll say that let's Google on their phone. If you have Google on your phone, which I know you do, can you look up the length of an eardrum?
Length of eardrum.
Would it be called eardrum? Or ear canal?
Eardrum, yeah. Oh, eardrum.
What did he search for?
Eardrum.
I want to know how far back your ear goes into your head. That's what I want to know.
Ear canal.
Ear canal, that's, yeah, not drum, yeah. 2.5 centimeters, wonderful. Okay, 2.5 centimeters. Right, so let's say we want to get a standing wave inside your eardrum. So it's like this, and that's the D. So what would be the wavelength? Yeah, 10. Okay, and let's say, what's the speed of sound? About 340? 330? Can you Google? We'll get the exact number. Speed of sound. Between 330 and 340, isn't it?
40.
It's 40, you think? 343. Okay. 343 meters per second. Small, quick calculation before we take a break. Give me the frequency here. Yeah, using the formula that we had. Yeah. I'll get something on YouTube once you've calculated the frequency.
How do you know it's 1/4 lambda?
Oh, because I'm saying I want a fundamental standing wave in the ear canal. That's what I want. Did you get the frequency? Uh-oh. What's the frequency? 3430? Are you sure? Guys, come on, what's the frequency here?
4 times 2.
B equals... What's the formula?
What's the
V over lambda. Frequency is V over lambda.
Yeah. So what did you get as the frequency? 34 hertz. Okay, let's see. How do I get numbers here? Let's just say 3.4 maybe. What do I want? Space. Painful to watch, I know. I do have YouTube on my laptop, but I don't have speakers on my laptop. K H Z. Search. Oh, dude, come on. 3.6. Close enough. Better. I won't blow your heads off, don't worry. Oh. Yeah. So I wait for the ad. Can I skip it now? Not as painful as I thought. I need to get a little bit lower.
Why are you trying?
Huh?
Not as painful as I thought.
I did this last year, but I guess I got a video that was closer to this. Quite painful, I assure you, if you were to listen to it.
I knew it!
Yeah.
I knew it!
Well, anyways, you can look it up on your phone while we take a break. If you can get as close to this as possible, it will not sound pleasant, because it'll be resonating in your ear canal. Quite unpleasant. Unfortunately, I couldn't do it.
Will it?
It won't explode, don't worry. Yes. Pop. Yeah, no, you're okay. You're okay. We'll take a break for